In this video, we would cover how integers are represented in C programming language. As you know, there are two types of integers, unsigned and signed integers. We would explain them from ground up to establish a solid understanding. We would also speak about the range of values they can have, and eventually we would also discuss mathematical representation of both encodings. Let's go to the whiteboard and start with the definition of unsigned encoding. Unsigned encoding is quite simple. Any value you have, if you want to store it as unsigned integer, you convert that number, that value, usually we speak in decimals. So you convert that decimal to its binary equivalent. So for example, here the 8, the binary equivalent is 1000. So we have 4 bits here. The minimal data type a typical C implementation has 8 bits. That is 1 byte character type. Now, if we want to store 1000 in 8 bits, what we do is we add 4 zeros before this to make it 80, and this is the binary equivalent of 8, and that's it. So if for example in our program we had this declared, and in our memory this is the location of this variable, then the value stored would be 0 0 0 0 1 0 0 0, and that would be 8, and that's unsigned encoding. So let's take a better example. Here we have 1 2 3 and we want to represent or encode it using unsigned encoding. And the obvious thing to do here, because unsigned encoding is the simplest encoding, is to convert it into a binary equivalent. By hand, if you want to manually do it, one trick is actually to keep on dividing 123 with 2 and keep on storing the remainder. So for example, here 123 was divided by 2, 61, and 1 is left behind as remainder. Similarly, 61 is divided by 2 with 30, and 1 is left as remainder because 61 is odd. Similarly, if we divide 30 by 2, we have 15 and 0 as remainder. Now 15 divided by 2, so we keep on going. We keep on going till we get 0 and nothing is left. And then we have all these reminders. So we take them in reverse. So the value would be 1 1 1 1 0 1 1, and that would be the binary equivalent of 1 2 3. Of course, you can use computers and internet to do the conversion, but this is a handy trick if you manually sometime have to do the conversion. Now 123, if you had a character X and unsigned character X in program equal to 1 2 3, this would be stored in memory as, if you see here, we have just 7 bits, so we need to append it with 0. So 0 1 1 1 1 0 1 1. So that would be the equivalent of 123 in memory, and this location is the location allocated by our runtime system once we load the program in memory. X for X. Let's take character data type, and it's an unsigned character data type, so it has obviously 8 bits. What could be the maximum value possibly we could store in these 8 bits? That obviously would be 1 1 1 1 1 1 1 1, because the value from this pattern of bits would be maximum. If you calculate that, usually it's done using weight. Each bit has weight. So this bit has 2 raised to power 0 weight, this bit has 2 raised to power 1, and it goes on till here 2 raised to power 7. So this would be 2 raised to power 7 plus 2 raised to power 6 plus 2 raised to power 5, and so on, plus 2 raised to power 0. And this would be 255. So 255 is the highest number which could be stored in an unsigned character. assuming that character obviously has 1 byte size. What would be the lowest number? Obviously, the lowest number would be all zeros. So if we have all zeros here, that would be the lowest number. And obviously, this would be 0 into 2 raised power 7 plus 0 into 2 raised power 6, 0 into 2 raised power 0, and that is 0. Now, that means that the range of values which a character, unsigned character, 1 byte can store goes from 0 to 255. Now, this would be different for different lengths. So, for example, if you have 2 bytes, then 2 bytes would be 0 to, we can write that down in hexadecimal. It's quite easy to write in hexadecimal. So this would be this range. And here, this essentially means all ones. So this value would be something along lines of 2 raised power 16 minus 1. Let's now generalize it a bit. And let's see if we have a W-bit data type, what could be the highest value? The highest value could be all ones, right? So this will have W ones. Now the value here would be 2 raised power, so this would be W minus 1 plus 2 raised power W minus 2, and go on till 2 raised power 1 plus 2 raised power 0. Now with mathematical binomial theorem, the summation would be 2 raised power W minus 1. Of course, the binomial theorem proof is outside of the scope of this video, but this is quite generic term. So for example, if you have 8 bits or 1 byte, so this value would be 2 raised power 8 minus 1, which is 255. Now for 2 bits, it would be 2 raised power 16 minus 1. For 3 bits, it would be 3 bytes, it would be, there is no data type with size 3 bytes, of course, but 4 bytes, it would be 2 raised power 32 minus 1. Now that we have discussed what is unsigned encoding, it makes sense to start moving to signed encoding. Now, signed encoding is particularly useful if you know that you would have some use for negative numbers. And to understand signed encoding properly, it makes sense to start from smaller data type. Now in C, the smallest data type is 8-bit long, a char data type, but let's for a second assume that there is even more smaller data type, and it's 4 bits. And if we, for example, write down all possible values for a data type which has just 4 bits, there are 16 of those. So that's why it's actually easy to imagine and play with numbers when you have less combinations to deal with. And with 4 bits, that's the case. And imagining everything, overflow, addition, inversion, subtraction, multiplication with just 4 bits is far too easy. And in binary representation, or particularly in integer arithmetic, the concepts do expand to bigger data types. So if we write down all unsigned numbers possible in 4 bits, now we have 0, 1, 2, 3, 4, and we wrote down all bit patterns. And as you can see, they have this increasing order. Now, you might also know that if we have to convert, for example, number 14 to its equivalent decimal number, we can check the bits which have 1 and then sum up the weights, corresponding weights. For example, here we have 2 raised power 0, 1, 2, 3. 3 plus 2 raised power 2 plus 2 raised power 1 plus 0, because there's no 1 bit here. So this would be 8 plus 4 plus 2, and that would be 14. But in signed encoding, we don't use the weight of last bit as positive. We use it as negative. So what we do is that we want a bunch of negative numbers. So instead of using keeping all the weights positive, we just flip for the last bit, and this bit is called signed bit. So for example, every time in all these numbers, every time there is a 1 in the most significant bit, that's a most likely a negative number. I'll tell you why. Say for example, this one here. So this is 8 if it was unsigned encoding. So this would be unsigned 8. But if we flip the weight of this number, this would be -8. What about this number? Here we flip the weight for this bit, so this would be -8 plus. Here we don't flip. We don't flip for these three. We just flip for the last most significant bit. So this would be 2 raised power 0, which is -8 plus 1. This is -7. Now say this one. So 11, if we had unsigned encoding, this would be 11. But if we have signed encoding, we flip the weight of this bit. So this would be -8 plus 2 raised power 1 plus 2 raised power 0. So this would be -8 plus 3. So -5. We start arranging these 4 bits from increasing order. Up until here, the most significant bit is 0. That would mean there is no negative weight. So all these values are same whether you are using unsigned or signed encoding. But then it flips, because as soon as we cross 7, the next pattern is 1 0 0 0. Let's check the range of values, possible range of values signed encoding can have for 4 bits. Say for unsigned encoding, let's write unsigned here. For 4 bits, the least value could be 0 0 0 0, and the most value can be 1 1 1 1. The reason for that is that each bit actually has a positive weight. So this one would be 2 raised power 3 plus 2 raised power 2 plus 2 raised power 1 plus 2 raised power 0, and that is 15. Now for signed encoding, the least bit won't be 0 0 0, because the least number actually, we already know the weight of this bit here is different, it's negative. So the least number would be if this bit was 1, because the contribution of these remaining bits are positive, so the least number would have them as 0. So the least number in signed encoding would be -2 raised power 3, which is -8. And the highest number would obviously be, it will have 1 in the bits placeholders where the contribution is positive. And this last significant bit, because it's a signed bit, the contribution is negative, so we'll put it 0. So this would be -7. So as you saw, the range of values for 4-bit signed data type would range from -8 to 7. If I write it in bit pattern, this would be 1 0 0 0 to 0 1 1 1. But for signed, it was unsigned, it was 0 0 0 0 to 1 1 1 1. Now let's extend this understanding to a real data type in C, and that is char data type. So let's say we have unsigned char data type and signed char data type. Now, unsigned char data type, the range would be 0 and, sorry, so the most negative number would have 1 followed by 7 zeros. And the highest number would be 0 followed by 7 ones. There is another way to write down this notation, this range, and it's a slightly easier way to deal with bit patterns. It's to write them in hex. So you could also write 0 cross. This would be 8. Yes. And this would be 0. So you break them down in 4-bit patterns and write the corresponding hexadecimal. So this would be 7, and this would be F. And for unsigned, it was the lowest number was 0, and the highest number was F. We can even extend it easily now. If we just keep on using these hexadecimal numbers, we can even write and deal with bigger data types, bigger data types which have bigger size. For example, if we have integer is 4 bytes, we can easily think about ranges without calculating their decimal equivalent, because calculating decimal equivalents is far too computation intensive, and I don't even remember what the number is, but you can write it mathematically here. So this would be 8, 0. So this would be 1 byte, 2nd byte, 3rd byte, and 4th byte. This would be the lowest number, 4-bit integer. So signed integer. And the highest one would be, so the most significant bit for signed integer, if we keep it 0 and rest of them ones, it would be 7 F, 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 F. If we mathematically have to write down these two encodings, we could write down them as well. For example, for all those of you who are quite close to mathematics, it makes sense to just realize what unsigned encoding is mathematically. Say you have a bit pattern, for example, X. It's a bit vector where the width of this bit vector is W bits. Now each bit would be, say, first bit is either 0 or 1, X0, and second bit is X1, X2, and so on. So the last bit would be X W minus 1. Second last would be minus 2. You see, the indexing we did would be from 0. So the last one is W minus 1, not W. Now this is a very generic number, right? So these this X0, X1, X2, these are variables which can have bits as their values. So for example, as an example, if we have 14, so 14 would be 1, 1, 1, 0. Now 14 here, this is X0, this is X1, this is X2, and this is X3. Now W here is 4-bit, right? Now we will use this pattern, this generic pattern, or a vector or a pattern of bits to write down mathematical formula for unsigned encoding. So mathematical formula obviously is that a decimal number which is equivalent to this bit pattern is the number represented by this pattern, right? So for if we have a function which converts a binary pattern to its equivalent decimal number, we just need to sum these weights up. So this would be x w minus 1, 2 raised power w minus 1, plus x w minus 2, 2 raised power w minus 2, up until x 0, 2 raised power 0, right? So mathematically you could write summation I would range from 0 to w minus 1, x I to I. Now this would be the mathematical formula for unsigned encoding. With a little change, we can turn this formula for signed encoding as well. So instead of adding all the bits, we just add these bits and keep this bit separate because this is the signed bit. So if we want to rewrite this as a formula for calculating signed integer, we could write. So for example, this pattern, for example, let's say it represents a number in signed encoding, and let's say 1110. Now this was 14 in unsigned encoding. What would be it in signed encoding? It would be, this would be -8 plus 4 plus 2 plus 0. So this is -2. We'll keep this bit as it is. X w minus 1, 2 raised power w minus 1. But we will have a negative weight here, right? The first bit has negative, and these we sum up. I from 0 to w minus 2, x, I, 2i. So this would be the mathematical formula for unsigned encoding.